It's just a great honor to be able to be the director of this innovation lab at such a critical time. And the title of the talk really sort of setting the scene for what I want to talk about. So it's research for development in a world of interconnected and gargantuan threats. And this is coming from a fellow Dubliner, Administrator Samantha Power. Both of us are from Dublin, both now US citizens. But she talked in her address or Senate hearing March 23rd about 4 interconnected and gargantuan challenges. This was the time when we were writing our grant to be an innovation lab, which went in on May 10th. And she was talking about climate change, COVID, conflict, and democratic backsliding. And then it was approximately 29th of February or 28th of February 2022 when we saw the Russian invasion. And even she, as a well-versed European in political science, couldn't have expected that we'd also have war in Europe on top of all of those other challenges that we face. So our lab is really setting the scene or being established during this particularly difficult time. And today's report from the State of the Food Security and Nutrition of the World from FAO, as expected, we continue to fail. We now have as much as 828 million people who are food insecure. And this is the 5th year in a row where it's increasing. So I'm including 2022 in that, because we're obviously going to have an increase in food insecurity. This is the 2021 data. And the expectation, and this is amazing to me, the expectation is that by 2030, maybe 8% of the world's population will be food insecure. It's currently 9.8%. That's the same percentage as it was in 2015 when we set the ambitious Sustainable Development Goals. So in 15 years, we won't have moved the needle, which I find to be absolutely terrifying. And perhaps like Administrator Power, the Irish have a very strong disgust and anger towards food insecurity and inequality broadly. And so that's the framework for us setting up this innovation lab. So we come together as a consortium of partners with Penn State being the management entity. And I wanted to get into some of the work that we've been doing today in doing research for this critically important topic. So just to remind you, we're only 10 months old, so use that as a contextualization for where we are. So given all the concurrent threats, we've really framed it as an SOS system, which is of course what you need in a time of emergency. So for us, SOS is surveillance, outreach, and solutions, circling our youth and gender model, about which I'll talk about, and encircled by the biggest problem in town, which is climate change, and how we're going to be able to operate in a climate changed world. So surveillance is critically important because of the unpredictable nature of the threats that we have to face going forward. And research is critically important as we have to learn how to build the airplane as we fly it. And so we need to have research outputs reaching hundreds of millions of farmers in a very short period of time. Now, we came into this innovation lab as PlantVillage, which is a pre-existing system that I had developed after I gave up the evolutionary biology work, or in tangent with that. And what it does is it leverages artificial intelligence to help smallholder farmers like Rosalind here in the foreground, who's a lead farmer, help her neighbor Emiliana. And so what it's doing is providing a human level expert diagnosis, in this case of cassava mosaic disease, in the field, in a phone, offline, very effectively. And the same thing here for fall armyworm. And so we took this technology back in about 2018 and we gave it as a global public good to the United Nations. I was a fellow at FAO on my sabbatical. We built a suite of tools for FAO, as well as CG centers like IFPRI and IITA and others. And so this platform is in over 60 countries and 30 languages, which is well suited then to be this transboundary pest tool for USAID as an innovation lab. And we've had a number of successes before having come in, and perhaps those successes are part of the reason why we've been able to have the honor of running an innovation lab. But one of the major successes was in the desert locust crisis, which was a crisis within a crisis, because it happened during COVID, when we had the global shutdown and the inability of experts to travel from location to location. So during the peak of that, we were reaching about 16 million people a week in Kenya and Ethiopia. And we were critical to saving food for 40 million people by being able to pinpoint where the swarms were with the technology, and then enable county governments, regional governments, and FAO to coordinate responses. So as the locust crisis moved on, the drought intensified. So we're in the worst drought in East Africa in 40 years. And so we're using the same approach to scale out, in this case to 8 million people in Kenya, 5 million in Burkina Faso. And we see that the scaling out of climate change adaptation advice has about a 92% effectiveness in changing behavior. So it's really, really useful to see this technology designed for one opportunity being used for another. And so the surveillance is critically important, and I want to come on to aspects in this talk of the research that we're doing and what are we actually working on currently. So all of us are involved in moving the ball from one side to the other, but as we're finding, and as the report demonstrates, we're failing. So what are the reasons for this? Well, there's multiple interconnected barriers to this. Now, the framework here is that research is critically important. So yes, we should have research, and these are research pillars to help us get from one side to the other, but there still remains gaps. And I like this model that I sort of borrowed from Zach Stewart, which I think is very effective, but not an original model. It's what the land grants are built on. It's to combine research and extension. And in this way, we can go from one side to the other. So we must have research pillars, but at the same time, we must be scaling that out to tens of millions, if not hundreds of millions of people who are in feed the future countries. So today I'm going to talk about 3 vignettes on our research, just to give you insights of what we're doing. The first is integrated pest management research at scale in a climate change, broken and sludgy world. I'll get onto what that means later on. And because the world is broken and sludgy, we need rapid response systems. And then because the world is unpredictable because of climate change effects on crops and biotic stressors, we have to do surveillance because we don't know what we don't know. So part one, we've been incredibly motivated by Mooney at the IPM Innovation Lab. And what he said in 2016 is that the key issue regarding IPM technology transfer is how to cost effectively spread IPM to a global audience of millions of farmers in enough depth so that they will adopt IPM in an appropriate manner. So I think these 3 aspects are critically important: cheap, millions, and meaningfully affecting behavior. So the first thing I wanted to show you was this multifactorial experiment on maize performance across diverse agroecological zones. So we started on 2,000 fields, but the idea is to go from 2,000 to 200,000 to 2 million in 3 seasons. And so we combine multiple components: climate smart advice, and then the application of biochar, which is micro capture of water near the root hairs, which are critical for droughts, fall armyworm control from ICIPE, striga weed control out of Montana State, now a company in Kenya, maize leaf necrosis from CIMMYT, and intercropping from ICIPE and CIMMYT and others. And this is all led by our sub-awardees, Dream Team Agri Consultancy, which is a local enterprise in Kenya. And so from this multifactorial approach, we've got a number of hypotheses that we can test. The first was that the effects are multiplicative, not additive. So maybe fall armyworm interacts greater with intercropping than striga weed control, for example. And another one is because we're doing 2,000 fields across 10 counties, agroecology probably plays a critically important role, and it's very decisive. So we're also testing that. And the third element is farmers are likely to pay for some, but not all inputs. So the work is started in February, January, February, across 10 counties. And so we're still daily collecting this, but this is just some of the early results. So again, 2,000 fields. We've only collected about 120 of those fields so far. But here's the difference. Here's the IPM package here, and here's the control. And Kenya is in the worst long rains in 2022 of 70 years. So it's in the worst drought in 40 years because it's a successional drought, but this particular long rains is the worst in 70 years. And so here's the effect that we're seeing. Very, very good maize here compared to the controls. And here's some of the data where we can start to explore. Again, still coming in rapidly, but our objective is to look at this in increasing detail to sort of tease out the parasitoids versus other approaches like MLN, maize leaf necrosis resistance versus parasitoids or other treatments, and to see what is driving the yield gains. Because from these drivers, then we can start to understand aspects of things that we're going to do in the second stage and the third stage and the fourth stage. And so a lot of this is going to be pulled out with either standard regression models or machine learning environment. And a critically important part is a genetic effects. So we have a variety of different seeds coming in here, and some of them, which are DK777, are tolerant to maize-leaf necrosis, but we're likely seeing a breakdown in tolerance based upon the data that we're already seeing coming in. Overall, we're seeing about a 70% increase in yield due to the package we're deploying, but we'll then discriminate whether that's driven by parasitoids or biochar or climate change advice, or and so on and so forth. It's not just the data that we've collected, though. Part of what we do is pull in about 40 years of data from NASA FuseNet, as well as data on net primary productivity from MODIS and Landsat and other sources. And this is also going to be part of our analysis, including with soil. So tomorrow we're having a training with Land PKS for our team in Kenya, so they can start to include Land PKS data into this. Now, the critically important part is that the training will happen for these young people on the ground, the dream team. And these are a critical aspect because none of us on the team have been in Kenya implementing this research trial. All of this happened since January, because setting up an innovation lab in the current environment where there's a lot of difficulties in bureaucracy means that we can't travel, and a lot of aspects of COVID, even in January, February, prevented that. But we were able to operate effectively with the dream team, which was in a model that we inherited from the locust crisis, where international experts from FAO were not able to travel throughout the affected regions, but the dream team were. So this is an effective model that we were able to implement. Now we're able to now explore how those dream team respond across the different counties. So what is the difference in frequencies here, or the slope of these lines across the 10 counties? What drives this? So we can study the effectiveness of the youth team. Now, that is not to say that the youth team there, who are completely operating independently, are not alone. So this is the team yesterday. This is Serge, who's on the call. Serge is an agronomist. Edward is a data scientist. Derek is a data scientist, Derek Moore, and Vipana here is an agronomist and data modeler. And so this is yesterday's picture. And then this is from this morning, where we were presenting what we're doing to the dream team. So you have that iterative learning, because the issues around remote working allow us to break through lots of these aspects of sludgy conditions to prevent effective working together. The other component that we're studying is behavioral economics, and this really predates. So sludge is from the book on sludge, and which is also from the book Nudging, from Cass Sunstein, and this is something that we've been interested in for a number of years. So this predates our innovation lab work. This is driven by Meta Uppala, who's a sociologist associated with PlantVillage. But here we've been looking at the farmer groups and the network ties and asking questions when they're told about things which are new, like IPM. What degree of spillover do we find, and how well is that being percolated throughout the system? And we're finding that new ideas like IPM versus older ideas like conservation ag are being percolated at a higher rate. And moreover, when farmers who are lead farmers have more effective ties, whether they're family or church or neighbor ties, this is likely to lead, and this is not a new idea, this is the fusion of innovation research, which has been going on for a number of decades, but we're able to sort of formally study it now at scale. So another component of this picture, the dream team, the farmer, but it's also here. This is also an intelligence. We have intelligence here and intelligence here. This intelligence here doesn't get onto the field very much, but they are effective because they're connected. But this one is truly a new intelligence, and that's a lot of what we're doing. We're pushing forward new research in artificial intelligence, and this is something here from our lead AI engineer, Pete McCloskey, and this is looking at a segmentation model, and I'm happy to go into details of what that actually means, but it's a new, more powerful tool to AI that allows this tool to become faster and more powerful over time. So that's the research of IPM at scale, given the constraints we have. And none of us expected that an additional constraint would be the invasion of Ukraine by Russia, which is happening at the same time that we're having the worst drought in 40 years. So here we have the FuseNet reports, and here we have, of course, the invasion. And so this allowed us a unique possibility, which is to integrate other information. And so what we're trying to do is pull in the data maps on soil data. So we're trying to respond effectively to the current crisis by adding more information. So as I mentioned, tomorrow we'll have a training from Land PKS for the Dream Team, but we've already integrated the 30-meter soil maps into our system, which allow people to know, based upon a probabilistic machine learning model, what is the soil underneath their feet. But a critical addition is the application of this biochar fertilizer, which we only implemented back in March in response to the drought, understanding that fertilizer prices were already going through the roof. And so this is from Eastern Kenya, Kilifi. So we've been pushing forward this technology of Zai pits from Burkina Faso and the Sahel region, where we worked with farmers, we dug these, and then we put in the biochar, increasing the access of water to the roots and increasing the water holding capacity of the soil. And the results are dramatic. These fields are side by side, planted on the same day. This is the one with biochar and Zai pits, and this is the one which is a failure. Now, behavioral economics is really important here, because despite Kilifi having so little rain and being so ill-suited to maize, the farmers are very unwilling to let it go. So we have to recognize the reality of that and then implement solutions that allow them to adapt to the circumstance, while also moving towards more climate change adapted crops. So that was one of our rapid response systems that we were able to implement midstream. And I think that midstream part is so critical, because none of us in Penn State were on the ground in Kenya. It was the Dream Team who were on the ground, able to feed back this information, work with us on possible ideas, and then put it forward mid-stride, which is pretty impressive. The second one was potato. So we had heard about this research from IITA on wrapping the tubers in a way to protect against nematodes. And we recognize that the nematodes, the control systems are more expensive now to get, and also farmers are not using them. So we wanted to implement this IPM approach of wrapping it in this banana paper to act as a mechanical barrier. And this was on April 29th that we started this. And again, well after the Russian invasion, knowing the effects that we're seeing on fertilizer prices and pesticides and nematicides. This work is still very much in data collecting mode, but just to see that we can already start to see things popping out, like various treatments. This is just on the wilting behavior, but we'll see the actual tubers. But again, a really nice example of being able to have adaptive research run on the ground without all the sludgy effects that are contained by moving anybody from a university in the US to a field site in the Feed the Future country. And just we had Zach, our alternative AOR, in the field there last week with Annalise and then the Dream Team run by John Shalal here, and WinKit. Really delighted to have him, and also collaborators from IITA. So it's really exciting to have him there. So the third element, so we have IPM at scale, and then the other is being able to respond rapidly. And the third element is, how do we understand what's coming down the pipeline? And so for us, surveillance is critically important. And there's two components of that. One is genomic surveillance and doing research on genomic surveillance, because evolution being what it is, there's always more virulent pathogens or drug-resistant pests that we have to worry about. And there's also advanced research that we have to do in terms of integrating research on different sensors, which are cameras from 30 centimeters away to 700 kilometers away in terms of satellites. And so these are just some slides that I borrowed from our collaborator, Diane Saunders at the John Innes Center, and Dave Hodson at CIMMYT, who've had a sub-award as a quick start. And this is them looking at fungal diseases in wheat. Of course, wheat is critically important now because of the Ukraine crisis. And what they have been doing is developing these rapid response systems, which are using between 200 and 400 genes to analyze the pathogen, determine its phylogenetic position, and then be able to determine if it's a new or emerging threat and whether it's resistant to control measures or not. And so for most Feed the Future countries, the ability to get a genetic test usually is about 6 months turnaround. And these nanopore technologies are really effective because you can have 2 days from sample prep to results completely independently. And then you can integrate that into a forecasting system. So they've been doing forecasting across Ethiopia and Bangladesh and elsewhere, reaching millions of people. And a massive success in Ethiopia last year, despite ideal conditions for the disease, they were able to effectively anticipate it and then effectively respond to it. So it's a mobile rapid response lab. So what we wanted to do was see if we can get that into our current system, and particularly into where we were working in Nepal, which is one of the countries we were working in. So it's a simple prep, no cold chain storage, happens in the back of a car, runs on batteries, no internet, because the bioinformatic platform is built into the local laptop that they have. And so then partners are able to run this locally and have that result in a very short period of time. So we did this Marple deployment at the NARC campus in Nepal with our IDE partners, which had worked with previous innovation labs. We trained 22 participants here, and it was really, really effective. And so here's some of the results that we see from this. So what they found already, and this just happened in April. So what we found already is that a lot of the races that we're finding are non-surprising. So they're Nepal, they're South Asia races, and this is critically important. And why would we say that? Well, we've all gone through 2 years of COVID, and we understand things like Omicron, which has huge numbers of genetic changes, which is why it's got a long branch here. And there's a variety of different approaches here, like long branch attraction and phylogenetic analysis. But this is the reason why it's evading all our vaccines, because it's evolved to do so, to sidestep them. And so what we want to eventually do for not just wheat rust, but all pathogens, and this one is for yellow rust, we want to have this for all countries, so they can do in-country DNA diagnosis and then understanding the extent of evolution in real time, so they can then determine whether the local tools that they have, let's say it's a fungicide, are able to counter the threat, or what other approaches that they have to take. So this is, again, from Diane Saunders' lab, and really, really excellent work that mimics what we have done substantially in human pathogens. Okay, so our next step is to look at the bridge between the Himalayas to East Africa. So a lot of the pathogens are moving across here. Again, Omicron is a story from South Africa out across the world. So it really does drive home the point why we need a global surveillance system fully connected up. So we'll be continuing this, and there's a lot of interesting aspects about Nepal, particularly alternative hosts like Barbary, which are leading to hotspots of sexual recombination. So again, this is probably where we got Omicron from. A lot of evolution inside the body of an immunocompromised individual led to that very, very different pathogen coming out the other end. So lessons from human biology that we can transpose. So surveillance is, in addition to being in the phone, surveillance is also something we can do in the phone. So what we're doing here is leveraging the power of AI in order to educate farmers. But from this, we can also bring that data in and then combine it with satellite data. So we're pushing forward the frontiers of AI in the phone. And again, I can speak separately on this. But I think that the critical element here is, once it's educated Rosalind and Emiliana, there's a lot more we can do with that. So just to give you a real-time demonstration of this, this is our Ag Observatory. So this is for all Feed the Future countries. These are our crop water balance models I'd mentioned before. This is the daily FuseNet data, which is coming into our system that everybody can see updated or sent to email. And then here we can see our analytics platform. So we can look at any of these samples coming in. So if we look at cassava, for example, and then we can just type in Kenya, so you can see this locally, and then you can zoom into the individual field. So it works offline, but then we're able to pick that data up. We can correct it, we can look at it, we can send a message directly to the user, and then we can pull it into this component here, which is our Ag Observatory, and we can look at locations where, for example, Kakamega County, where we've been doing a large experiment as one of our USAID counties, and we can look at records which are coming in. And so let me just go to one of them here. This is from 7 hours ago in Kenya. And so we can see the individual farm here. And now what's happening in real time is we're pulling in satellites from crop water balance models. We're pulling in CHIRPS data, which is a satellite looking at the cloud. We're running a specific crop water balance model here. This is 2 satellites, MODIS and Landsat, which are being delivered by UNFAO WOPR system. So we can look at above ground biomass. This one is perhaps the most important, I think. And so I'm wearing my NASA t-shirt today. This is NASA SMAP, which is soil moisture. And in a world threatened by drought, it's critically important. And we see this field is decreasing. This is forecast here. And then we have the actual picture from 7 hours ago that I can show you in a talk. And so we can begin to integrate the data we have from satellites with the phenotypic data, and then ultimately the genotype data that we might get on the host resistance genes coming from the work that Diane Saunders and others are doing. And so we'll have the full package all together in this system, which again allows us to do the type of machine learning results to do better forecasting and better predictions. But essentially what it means is these supercomputers in the hands of young people all over the Feed the Future countries are many eyes to find new threats. But the unfortunate point is that we will have new threats. And USAID has been looking at this over the years: maize leaf necrosis, striga, fall armyworm, locust, and then et cetera, et cetera. So we really do have to constantly do the surveillance in order to see what's a threat we have to deal with today and what's coming down the pipeline at a more later date that we can kind of put off. So in conclusion, the sort of prognosis from administrator power seems a little bit terrible. And even, as I mentioned, she would not have predicted the Russian invasion of Ukraine and all the downstream effects that we're all struggling now to deal with. But I think there's a hope of optimism in her first address to staff, and I think it talks about taking a moment in history that is demanded, and it is the joining together of research capabilities that outflow from the US land grants at such a wonderful rate and are so capable for dealing transparently with problems, and combining it with other aspects of US ingenuity, and particularly the software systems and the AI systems. So for those of you who know Penn State, an alternative name for it is Happy Valley, since we've sort of been depression proof ever since the Great Depression. So there's the framing there is Happy Valley. And so for me, I've often thought about the land grants as being the great emblems of what the United States has been able to achieve. But if you combine Happy Valley with Silicon Valley or any of the land grant universities, then we have the best of 2 components. And I think this is the optimistic outcome that I think we should be focused on. Things are horrendously bad, let's not kid ourselves, but technology is such, and the capability to work real time with youth in the country, in the Dream Team, are such that we can respond adaptively and also perhaps take advantage of the crisis. There's a political scientist, Ian Bremmer, who talks about the value of these crises in responding. So we can take the advantage of this crisis over the next 2 years, particularly with stimulus funding, to come out of this more resilient. So what are the mechanisms we can put in place now that can turn the tide? Because if we don't take the risk that this moment in history demands, then the very unfortunate reality is in 2030, we won't have moved the needle in 15 years on global food security, which will be just an extraordinary tragedy and collective shame upon all of us. So many acknowledgements. There's a huge group of partners in our quick wins. I haven't talked about a lot of the research that they've been doing. I Of course, the main acknowledgements are to USAID for betting on us, which we really do appreciate, and the extraordinary support we've had from our AOR, Angela Records, and our alternative AOR, Zach Stewart, and really just as newbies educating us along the way, which we've really helped. For my own part, I couldn't do anything without an extraordinary team here at Penn State, who are just wonderful, and these are the people here. So with that, I wanted to sort of stop sharing and thank you all for your time and patience, and happy to continue in the Q&A session. Thank you so much.